but I hope you like it. We can start with your presentation. So welcome again, Dr. Xiaoyi, Jiang. It's a pleasure to introduce our speaker for this session at the conference. Dr. Jiang is an extraordinary individual who has made significant contributions to his field of
graph concept in chemistry, bioinformatics, and more. Okay. Another application case, clustering. Clustering is a key issue in data science, and here you see some points, and they are clustered into three clustered, represented by three different colors, green, blue, and red. And if you have worked on clustering, then you know clustering is a very delicious issue in the sense it's very unstable. Yeah, it's not easy to obtain high quality clustering. For that reason, ensemble computation is a very nice concept to deal with this uncertainty. In this way, we have some data set, we obtain one clustering result using whatever method, we obtain a second result, and so on and so forth. We obtain in total m results, and you see each result means some different partitioning of the initial data. And then we apply the concept of generalized median or consensus computation to obtain a final clustering. And typically this final clustering, if this is well done, has a higher quality than the input clusterings. And you see such application in remote sensing. And here the data, the details are not important. I just like to share you with some of the key ideas here. You see some data. You see illustration of different clustering results obtained by this very simple method of k-means. You see the first potential clustering, the second one, and so on and so forth. And then they are combined together to obtain better clustering results. As said, this has some application in remote sensing. Okay. Actually, this can be, clustering is so widely applied so that it can be applied so that the ensemble computation can be used for many different domains. One such case is bioinformatics. You see here I'm not an expert, so I will not go into details about that. This is clearly something for bioinformatics, and you see here, the concept here is consensus clustering. Okay, and not only clustering. I'm not sure whether you have heard about this. If not, then it may be an interesting concept for you, the so-called bi-clustering or co-clustering. In case of clustering, we have features, and based on the features, we cluster data into different clusters. Okay, but in case of bi-clustering, the key point here is we do not consider the features as given. We consider that different clusters may need different features. So it's a clustering in two directions, the clusters themselves as before, but also the clustering of features. There are many situations in practice where bi-clustering is needed instead of the classical clustering. And here is a very new paper and saying it's time to apply bi-clustering for bioinformatics, and it's quite sure we also should apply consensus computation for bi-clustering, because bi-clustering is even more difficult to obtain than the classical clustering. Okay, and so far you have seen some examples from different domains, starting from numbers, 3D rotation, and clustering, and so on and so forth. And now I like to say some words about domain-independent methods. These are methods that can be applied basically to any domain. And we have published recently this year a very brief survey on that. We have tried to make a taxonomy of existing methods. You see different ways of generalized median computation, and you can do it by some mathematical optimization. You can apply some search space, and you can start with some initial solution and try to iteratively refine the initial solution. And another specific kind of solution is space transformation. And we have been working on that. And I like very much this general approach. Actually, this behind it, it has a very general problem-solving technique. If you have some trouble in one space, then please try to transfer the problem into another space in the hope that the problem can be better solved in the second space. Given the solution in the second space, then you can go back to the original space. Exactly this happens here in this case. We have data, we have objects here, and because the generalized computation problems, they are often NP-hard, very difficult to compute, then let's try to go into vector space. It means we map each object to a point in the vector space. There are different embedding methods. And given the embedded points, it's quite easy to compute the min vector in the vector space. This is really easy. And given the min vector, then we need to go back. We need to map the min vector back to the original space to obtain the generalized median in the original space. Okay, here again, the three steps: embedding into vector space, solve the problem there, and maps the median point or median vector back into the original space. Okay, the easiest step is this one here. It's a very simple one. This is okay, it's very doable. The last step is really difficult. But still, overall, it's doable. And actually, we have published this paper this year based on the so-called kernel concept. I will not go into the details, but exactly we follow this approach using the kernel concept, and we could show that it provides state-of-the-art results in several domains. And we have this library for public use. And yeah, actually, we have showed the application of this approach in different domains like strings, and some other colleagues have been working on graph, clustering by clustering. The overall message here is all the problems, they have high complexity. Many of them actually NP-hard, so we need to compute approximate results. This embedding, vector space embedding, can be very useful one for such a situation. Again, because this is a general problem-solving technique transformed to another space, in this case, transformed to a vector space, and probably this idea can be used for you in other situations. Okay, and I like to share with you some additional applications and also introduce some additional issues. And one application in medicine is to compute the so-called atlas. Atlas is basically some kind of, let's say, average model. The idea is to collect, I don't know how many, 100, let's say 100 brain images, and then to compute the atlas. This is average brain image. Yeah, here you see the partitioning into 3 age groups. In the first row, you see the brain of a young person, and here is the brain of middle-aged, and here is the brain of older person. And here you see the different atlas models. And there is one issue here. And typically, an image is considered as a point in a vector space, because in images we have rows, we have columns, and we can put all the rows together, yeah, to obtain a very high dimensional space point. So let's say if we have a dimension 100 and 100, and then basically we have 100 times 10,000, yeah? Then each image is in a point in a 10,000 dimensional space. And the issue here is the 10,000 dimensional space not only contains brain images, but it contains images of many other classes. So the point here is, if we collect how many? 10, let's say 10 brain images here, and actually the brain images, they only build a subspace, brain subspace, the so-called manifold of this high-dimensional vector space. But if we simply compute the averaging in this vector space, we obtain something here. This is simple averaging in a vector space. But we need to do something so-called manifold computation, because we need to restrict the computation within this brain subspace, the brain manifold. This can be very demanding, and actually the method here is exactly the computation restricted to this brain manifold or subspace. It's mathematically quite demanding, but important because it's necessary. You see here the computed atlas using this manifold computation techniques here on the right side. The left side shows the images computed by simply averaging the brain images in vector space. So obviously this is a better result than this one. Okay, this just leads to the consideration we should consider manifold treatment. And this is not only here the case, also if, for instance, if we deal with color space, the same happens there as well. Okay, and another application, I actually showed you such example at the very beginning, how to combine different ethnic segmentations to improve the segmentation quality. Here you see again 2 examples. The first is combining human segmentations. Here you see 4 examples here, 4 images. For each one, you see different human segmentations done by medical experts. And here in the last column, you see the combined result. Okay, the combined segmentation overcomes the different drawbacks of the individual experts and gives us a very nice overall segmentation. Okay, here you see example of combining human segmentations. On this slide, you see it's a very new work, and from this year, published from this year, it's about combining automatic segmentations. Here, given this image, you see 4 different deep learning models. Yeah, the details are not important. If gives us some segmentation here for the so-called, what is called typos plus, doesn't matter what it is. This is this kind of objects, and then they just combined the 4 results and to obtain this one. And the same happens here on the bottom to determine the nucleus. Again, 4 different deep neural networks applied, and to obtain 4 results, they are combined together to obtain this one. And they showed that in their publication, the combination results are better than all the initial segmentation results. And I also like to share with you some applications in machine learning. And here you see the stochastic gradient descent, which is fundamental for optimization. It means for, let's say, training large size neural networks. And there is one interesting result here, mathematical result here. And because it's iterative, we have a sequence of results, the small letter here. And here, x1, x2, if we start with some initialization, x0, then we have some result x1, x2, and so far and so forth. And you can consider this original sequence, but you can also consider this sequence, yeah, here, capital letter by x And this is nothing else than the averaged results of this initial sequence. The mathematical result given by the two mathematicians says that this sequence converges faster than the original sequence. Yeah. So indeed, this has found application in deep learning training, as stated in this very famous deep learning book you see here. Yeah. Okay. And here you see two other applications of averaging in machine learning. Here, in this case, averaging weights. And in this recent PAMI publication, they consider some particular domain of data, and so that manifold computation is necessary. So that this is a key issue in the design of this deep neural network. Behind all these works, the averaging concept is applied. And another application, because this SGD is just a technique for optimization. Optimization is essential not only for machine learning, but also, for instance, for image processing, for image registration. What is this? Here you see, probably better, let me show this second example here. We have two images. This is a PET. This is functional. We see some tumors here. And here we see CT, it's anatomic. And we see the tumor very clear in the PET imaging, but we are not sure about the organs, where the organs exactly are. We know approximately where the organs are, but not so sure. In CT, we see the organs very well, but we do not see the tumors very well. By registering the two modalities, we see both. In this combined imaging, we see the marked tumors, and we also see clear the organ. But for the registration, we need to know the geometric relationship between CT and PET. So, yeah. So this is mathematical optimization, and where this can be very helpful. What I've shown you is, instead using the first sequence, you should better use the second sequence, which gives you a speed up in convergence. And this work basically shows this aspect. There are also some theoretical aspects. I will not go into the details, but just like to give you some impression. So, well, I showed you this formula, basically. Yeah, again, the notation differs slightly, but it's the same formula, same mathematical definition. We have objects, input objects. We like to look for some median object in space U, and the distance function is represented by this symbol delta. And this is a simple definition. You may ask yourself, what are we doing here, actually? What we do here is maximum likelihood estimation. Yeah, we assume some distribution of data, and we can show, given that data distribution, and this computation exactly means a maximum likelihood estimation, which is a general optimization concept in statistics. Yeah, okay. We have the details here in this recent work. And another issue of very broad interest is robustness. Well, if you compute the average of n objects, but in case you have some outliers, which are objects far away from the majority, what happens? How do the outliers influence the average computation? Well, this is related to the so-called breakdown point. I will not go into the mathematical details, but intuitively we can understand it this way. Is the computation tolerant to how much percent of outlier or outliers. There's very interesting result here. This is so-called breakdown point. We can show that if the distance function d is a metric, then the generalized median computation has a breakdown point of 0.5. It means the computation can tolerate up to 50% outliers without substantially influencing the computation. Yeah, and actually you can see it here, and you have see at the very beginning of my talk the two different definitions of distance function. This one, then we have this average, and this one we have median. And it can be easily shown that this distance definition is not metric. Non-metric, it means this computation is not robust. It has a breakdown point 0. It means one single big outlier can totally destroy your average computation. Yeah, I think it's quite well known. And here, if we use this one, and this one is a metric distance function, so the median is robust one. It can tolerate up to 50% outliers. We also know that. And given this theorem, and then we have a mathematical interpretation why, or mathematical understanding why this happens. Yeah. Okay. And I like to come to end of my talk, slowly at least. I like to tell you some additional definitions of media. I use this definition here, but sometimes people use square, but doesn't matter. It's more or less the same. And we can compute the median not considering the complete space U, but we can restrict the computation to the input set. This makes the computation much easier because we only need to consider each of the input objects and select one of them as a result. It's called set median. Its computation is much easier. And we can also introduce weights into this computation as done here. You see again this formula, but in each term, we just introduce some weight. And this is fundamental, for instance, for the exponentially weighted moving average, giving a sequence. And like here, you have a series of noisy points, and the red one is the original function, the unknown original function, and the blue points are generated using this red one and added with noise. And this yellow one is the estimated sequence. And actually, you just consider one point and at time t plus 1, and consider all the points from the beginning to t, 1, 2, 3 until t, and t plus 1, and compute average. But each data point before is weighted by different weights. Okay, you see the distribution of the weights. The first neighbor has a larger weight, the second neighbor has a smaller weight, and so on. With increasing neighbor distance from the current time t plus 1, the weight decreases. And you see here, it's a very nice smoothing technique for time series, but also very useful for machine learning, deep learning. This is exactly the concept behind the so-called momentum for neural network training. And this is just because training neural network means we need to compute the gradient function in a sequence. And this is simply applying to the computation of gradients of the loss function. And another definition is different from the initial one I gave you. And here we look for some ball, yeah, so that every object is within this ball. We look some midpoints, center, and some ball with some radius, and all the input objects fall into this ball, and we require the radius of this ball is minimum. Yeah. And this is the so-called center problem, has a lot of applications, particularly in bioinformatics. And unfortunately, the computation is NP hard. Okay. And then, okay, this is an overview of my issues today. And, oh, sorry. And so I have introduced this concept of generalized media and given you some examples in different domains. And I also shared some way this vector space embedding approach for a domain-independent solution. And I very briefly mentioned some mathematical or theoretical issues for this computation. Okay, so the overall, actually, I've shown this citation at the very beginning of my talk. Uncertainty is the real issue in practice. We encounter uncertainty in data. We encounter uncertainty in all our computed results, independent of which data, which methods you use. You always have some uncertainty in your result. In both cases, it makes sense to do this kind of consensus computation or ensemble computation. And this is actually my last slide. And generalized media is indeed a very well-established concept of consensus computation or learning. And well, my main interest in my research, also in my talk today, is that this computation can be done really in any space. In any space you can have, and there are different ways of computation, either in domain-dependent way or in domain-independent way. And there are already many applications. And I hope after this talk, if you are not aware of this concept, at least in the general form before, then you become aware of this, and you got to know some ideas how to do that, and probably you will find this concept interesting and try to apply this concept in your work. Okay, thank you. Thanks for your attention.
Thank you so much, Dr. Jiang. Thank you for this interesting talk. I believe all of us will learn a lot. So thank you so much. We will continue with the part of the section of questions, if you allow us. So the first question is, nowadays, are there research in neurology for mapping neurons structures using these techniques? If yes, what cases?
Could you, I missed the first maybe part of your long sentence. Could you repeat the question again? Sorry.
Yes. Nowadays, are there research in neurology for mapping neurons structure using these techniques?
Oh, unfortunately, I cannot give an answer to that because it depends, because I'm not working direct in that area. We were collecting related literature for this survey paper, but we noticed it's so broad. We encountered so many application errors, and so far we are still not able to write a real survey paper. That's the reason why we publish a brief survey only. So our coverage of literature so far didn't or does not consider this area before. So I cannot give a real answer, but I would claim the following: either it has been done in this in that area, or it's worth doing.
Okay. Okay, so if I understand very well the second question, in terms of performance, which is the difference between the techniques, I think the previous techniques, and deep learning techniques?
Well, it's well, this topic is not about deep learning. Well, deep learning is also a huge field with many different techniques. And the generalized media is a technique of combining results. As I should, let me go back to probably this slide. Okay, here, if we apply this technique here, then it's useful for learning neural networks. Actually, it's useful for optimization in general, because this technique is for optimization. It can be used to train deep neural networks, as here, and it can also be used to different issues related to deep learning. So I would say deep learning is one area that has many issues, many aspects where this generalized and medium computation can be used, but the same can happen in many other fields. It's a general technique, not only useful for deep learning, but all for many other fields.
Okay, so personally, I have two questions more, please. Can you come back to the slide 11, please?
11.
Yes.
Okay. Why is so slow here? Yeah, you mean the definition slide?
Yes, there in the 11.
Yeah, here. Okay.
There, you are talking about measures of the similarity, but which measures are you using for your research?
Well, it depends very much on the domain. If you work with points, you have so it means for each domain you need to define some distance function. So there is no general answer, but there is no difficulty to define this distance function because it measures the dissimilarity. Yeah, if p equals to q, then the distance is 0. If 2 differs substantially from q, then d should be large. So in any domain, typically there are no distance functions. You just like to choose one of them. Let's say if I go back to this ranking example, in the literature, there are several very well-known distance functions between two rankings or two permutations. I don't think this is a difficult issue, but if you work with some space, yeah, in some space, then you have typically existing distance functions. If not, then typically it's not difficult to define such one.
Okay, thank you. And well, the last question in the slide 37, you mentioned that you use some deep learning models, and later you said, well, for the moment, it's not important to know which models they are, but just by curiosity, which models are you using in this kind of task?
Say again, which slide you use? 37.
37. Yes, in the slide 37.
Well, it's not, this work is not from my group. I just found this new publication here. You see here the 4 deep learning models. Unit somehow here, here. And the 4 models, they are very detailed described in this paper here. And for this nucleus detection, they use different 4 different deep learning models. Yeah. But actually, such details are indeed not important because, well, even the 4 models here, they are not necessarily the best one. I'm quite sure you can find some better models than these 4. And the key issue here is independent of the number, it's 4 or 3 or 5, 6, you can use some number of deep learning models to achieve the same number of results, combine them. Actually, in this case, the combination is done in a very, very simple way. Yeah, because in each pixel you obtain the probability. Is this pixel a foreground pixel or background pixel? They just averaged the four probabilities to obtain the final result. Yeah.
Okay.
The
Okay,
same
thank you
happens here.
Okay. Okay, well, thank you so much for really this interesting talk. I learned a lot, and I think all people, and I didn't know also the concept, so it's great to know about it. So we will pass to give you something symbolic, which it says la Benemérita Universidad Autónoma de Puebla, a través de la Facultad de Ciencias de la Computación, otorga la presente constancia al doctor Xiaoyi Jiang, por haber impartido la conferencia magistral Consensus Learning en el marco del V Congreso Internacional de Ciencias de la Computación 2023 de la Facultad de Ciencias de la Computación, celebrado el 4 y 5 de octubre de 2023. Pensar bien para vivir mejor. So, you will receive it by email. And again, thank you so much. It was so interesting. And well, it just says that today you gave the conference to us. You stay, and yeah, you will receive it in some minutes. Thank you so much.
Okay. Thank you very much for your attention, and thanks for giving this opportunity to share some ideas or some of my work with you. And I look forward to visiting your wonderful country in near future.
I hope you can do it. It's a beautiful.
Four times, actually.
Okay, we hope you can do it. I think it's a really beautiful country, and you are more than welcome.
And I wish you all a further successful and interesting Congress. Okay. So have a nice day.
Thank you so much. Have a nice day, you too.
Bye bye.
Gracias. Bye bye. Pues gracias a todos. Creo que ya.
Bye bye.
Bye bye.